To be able to understand that, we need to first review the atomic structure and valence electrons. You should recall that atoms are made of protons in the nucleus plus neutrons. So protons, remember, you have a charge of +1 charge and a mass of 1. Neutrons have no charge and a mass of approximately 1 as well. So these two subatomic particles are in the nucleus of the atom, and then surrounding the nucleus are electrons. Electrons each have a -1 charge and very little mass. So it's the number of protons that defines the element. Any element that has only 1 proton is hydrogen. Any element that has 6 protons in the nucleus is carbon. So carbon atoms always have 6 protons, and a neutral carbon atom is always also going to have 6 electrons orbiting the nucleus. And the mass of the carbon atom is going to be determined primarily by the number of protons and the number of neutrons in the nucleus. So remember then, the electrons orbit, or they occupy orbitals around the nucleus. And an atom is actually mostly empty space because the nucleus doesn't occupy much space, and the electron orbitals define a vast region of space around the nucleus. Alright, so what about valence electrons? Well, when these electrons occupy different orbitals around the nucleus, so electron orbitals have different energy levels. The lowest energy level is called the 1s orbital. This has room for 2 electrons, and this is good enough for elements that have only 1 or 2 protons. Then when you get to elements that have 3 or more, then in addition to the 1s orbital, you now need a second energy level of orbitals, and these are called 2s and 2p, and these combined have room for 8 electrons. So what we call valence electrons are the outermost energy level or shell of electron orbitals. The periodic table of the elements elegantly organizes the elements by their valence electrons. Each row comprises of elements with a different level of valence electrons. So the first row of elements, hydrogen and helium, have only 1s. So these are 1s. The second row has 2s and 2p, and then third row has 3s and 3p. So as we go to further down in the rows, we'll end up with 4 and 5 levels of electron orbitals. And then each of these columns corresponds to the number of electrons in the outermost or valence layer of electrons. So in the first column, we have 1 valence electron. In the second column, we have 2 valence electrons. And then here in column 13, but if we're looking at the first 3 rows, it would be the third row. It has 3 valence electrons, 4 valence electrons, 5, 6, 7, and either 8 or 0 valence electrons. And here we're saying 8 or 0, and actually for helium it would be 2 or 0. This means that the outermost shell of electrons, or the outermost energy level of electrons, is completely occupied. The significance of this periodic table and the arrangement of elements in columns by the number of valence electrons is that the valence electrons determine chemical reactivity or chemical bonding. Any chemical reaction involves only the valence electrons. They never involve the nucleus, and they never involve, or hardly ever involve, electrons in the inner layers. Right? So basically all chemical reactions involve only the valence electrons, and so the number of valence electrons in an element determines how it is able to react. One other thing we need to understand before we discuss how carbon and its other partners form bonds is the concept of electronegativity. Electronegativity is simply how much an atom or the nucleus of an atom really likes having its electrons around. Okay? Oxygen is one of the most electronegative elements. That means that the oxygen nucleus really wants to keep its electrons very close to it. You will note that carbon sort of has an intermediate, sort of a middling value in terms of electronegativity. Hydrogen is a little lower than carbon, but pretty close. And so what happens is that when carbon, and here I'm going to diagram the valence electrons in carbon. Carbon, remember, has an atomic number of 6, so it has 6 protons and 6 electrons. 2 electrons are in its 1s, or innermost shell. So if we diagram just the valence electrons, it has 4 valence electrons in its outermost shell. Oxygen has 2 more electrons in carbon, so it has 6 valence electrons. 2, 3, 4, 5, and 6. Now, one of the keys to determining how elements react to form bonds, is an understanding that elements really want to have either 0 or 8 valence electrons. So carbon can either give away 4 electrons or receive 4 electrons, and oxygen really wants to have 2 additional electrons. And hydrogen has only 1 valence electron. So let's see how carbon and hydrogen might react. Carbon and hydrogen can actually share electrons. So a carbon atom can share its electrons with 4 hydrogen atoms, and because their electronegativities are fairly similar, what happens is that their electrons are shared almost equally between the carbon and hydrogen atoms. And these are now what we call covalent bonds. So every covalent bond represented by a dash between the 2 symbols for the elements, every one of these dashes now represents a pair of electrons that's being shared. This is a stable molecule because carbon now has 8 electrons and each of the hydrogens now has 2 electrons, so all of their valence shells are full. And so this is called a covalent bond when pairs of electrons are shared between atomic nuclei. Now carbon can also form bonds with oxygen, or oxygen can form bonds with hydrogen by sharing electrons. So that would represent a carbon bond with oxygen, and then maybe an oxygen bond with hydrogen. And so now this is a happy molecule. This is methanol. And here I want to point out that oxygen is highly electronegative. It really likes to have its electrons close about it. And it's much more electronegative than either the carbon or hydrogen. What that means is that even though electrons are being shared between the oxygen and the carbon and the oxygen and the hydrogen, the electrons are not shared equally. These electrons are spending more time orbiting the oxygen nucleus than they orbit either the carbon nucleus or the hydrogen nucleus. As a result, the oxygen nucleus looks like it actually has a partial negative charge. The hydrogen nucleus, it looks like it has this partial positive charge. And similarly for this carbon. And so the bonds between oxygen and carbon, or oxygen and hydrogen, are what we call polar covalent bonds. So they're still covalent bonds because their electrons are being shared between the nuclei, but because their electrons are spending more of their time around the oxygen, unequally shared, the nuclei acquire partial charges, and this is what we call a polar covalent bond. The other extreme is, for instance, something like between a sodium ion or sodium atom, which has a single electron in its valence shell, and chlorine, which has 7 electrons in its valence shell. So chlorine needs only one more electron to complete its valence shell, and sodium sort of has this extra electron that is all alone in its valence shell. And so when sodium and chlorine atoms get together or get in close proximity, what will happen is that sodium will happily donate its sole electron, valence electron, to the chlorine atom. And that gives us a positively charged sodium ion, since the sodium has lost an electron, but it has kept the same number of protons. It now has a net positive charge, and that is what we call an ion. And the chlorine, having accepted an extra electron, now has a net negative charge. So these are ions, and the sodium and chloride ions are held together by a strong ionic bond. The opposite charges attract, and so this is an example of what we call an ionic bond. So here are the 3 types of bonds: ionic bonds, polar covalent bonds, and covalent bonds, and they're all determined by what happens, how these valence electrons are shared or actually given away completely to a different nucleus.